In this video, we will continue our discussion on thermocouples and focus on cold junction compensation. Let's suppose that you want to design and build an autonomous underwater robot that can measure the change in ocean temperatures with depth. Your robot will take temperature readings with a thermocouple as it descends and ascends, and it will do this autonomously over a span of several days. In the previous video, we discussed the ice bath method of fixing the temperature at the reference junction. We can easily determine the voltage at the reference junction because we know it is at 0 degrees Celsius. However, is this really practical for the AUV that you want to build? Sticking an ice bath in an AUV is very impractical. And unless the AUV has an internal system that can keep this ice bath at 0 degrees Celsius, this method of forcing a temperature on the reference junction is not going to work. An ice bath method would be appropriate in a lab setting. However, another method of determining the temperature at the reference junction is needed for an autonomous underwater vehicle. So instead of using an ice bath in an AUV, we could use a method called cold junction compensation. In this method, the reference junction of the thermocouple is connected to a block, which could be a piece of metal or even a breadboard or PCB. Copper wires are then used as extension wires to enable a device to measure the voltage of the thermocouple. This block is what is referred to as a cold junction. However, unlike an ice bath, the temperature of the cold junction needs to be determined. How could this be done? Well, if you remember the concepts discussed in previous videos, you should now have a working knowledge of two other temperature sensors. For example, the cold junction is typically located in an environment that does not undergo rapid changes in temperature, such as in the inside of an AUV. We can certainly use a temperature sensor that has a slower response time, such as an integrated silicon linear sensor that also outputs a voltage. Let's discuss how a linear sensor could be used to obtain the voltage at the reference junction. This method is called cold junction compensation. The first step in determining the thermocouple voltage at the reference junction is to determine the output voltage of the linear temperature sensor. Please note that you cannot take the output voltage of a silicon linear sensor and use it as the reference junction voltage in the thermocouple equation that was introduced in the previous video. This voltage output only corresponds to the linear sensor itself, and it needs to be converted to a temperature, which is the second step in this process. We can determine the temperature at the cold junction by converting the output of the silicon linear temperature sensor to a temperature. Once the temperature is known, you can then convert this into the thermocouple voltage at the reference junction using a lookup table or equation. Once you perform this conversion, you can add the thermocouple voltage at the reference junction to the measured voltage to obtain the voltage at the hot junction. You can then use a lookup table or equation to convert the thermocouple voltage at the hot junction to the temperature at the hot junction. This is the method of cold junction compensation. You can also certainly use a thermistor to determine the temperature of this block. You can measure the resistance of the thermistor, convert it to a temperature, then convert that to a thermocouple voltage, which will be your voltage at the reference junction. Let's go over an example that demonstrates how a linear sensor could be used to determine the thermocouple voltage at the reference junction. Suppose we are using an MCP9701 integrated silicon linear sensor to measure the temperature at the cold junction. The MCP9701 has an output voltage of 848 millivolts. How can we convert this voltage to the thermocouple voltage at the reference junction using the information shown here? The first step is to convert the output of the MCP9701 into a temperature. Using the equation and data provided in the datasheet, we can easily convert the output voltage to a temperature of 23 degrees Celsius. Now that we know the temperature of the cold junction, we could use the lookup table for the thermocouple to determine the thermocouple voltage at the cold junction. First, we find the row corresponding to 20 degrees Celsius on the table. The temperature is 3 degrees Celsius above 20, so we find the column corresponding to 3 degrees Celsius. The intersection of the row and column show that the voltage at the reference junction is 1.373 millivolts. Now let's take a quiz. Cold junction compensation using a silicon linear sensor has revealed that the thermocouple voltage at the reference junction is 1.373 millivolts. If the measured voltage is 4.676 millivolts, what is the temperature of the environment at the hot junction? Please use the information provided in this slide to determine the correct answer from the choices shown. You may pause the video to work out the problem, and when you have picked out an answer from the choices shown, you may unpause the video to see the solution. The solution is 96 degrees Celsius. You now know the measured voltage and the thermocouple voltage at the reference junction. The sum of these voltages is 6.049 millivolts, which is the voltage at the hot junction. Using the lookup table, we can see that 6.049 millivolts is at the intersection of the row corresponding to 90 degrees Celsius and the column corresponding to 6 degrees Celsius. 90 plus 6 is 96 degrees. And this is the temperature at the hot junction. You should now be capable of going into the lab and taking temperature measurements with thermocouples. However, before you do, note that thermocouple voltages are in millivolts. This can be inconvenient since your measurement device may not be capable of detecting such low voltage outputs. Therefore, we need a way of turning a millivolt output into a voltage output. One way to do this is to use an AD623 instrumentation amplifier, which can be found in the lab. The datasheet for the AD623 may be downloaded from the link shown here. This datasheet shows how you can connect the AD623 to a thermocouple to achieve an output in volts. You have now been introduced to 3 temperature sensors that are available in the lab. Each of these sensors has its advantages and disadvantages. Furthermore, you could use a thermocouple with one of the other sensors for cold junction compensation. There is a 4th temperature sensor that we will briefly discuss, and it is the resistive temperature detector, or RTD for short. The RTD is a 2-terminal device that is usually made out of platinum. It has a positive temperature coefficient, and it has the benefit of having a linear output. What's really great about these devices is that they have an accuracy of 0.01 degrees Celsius, which makes the RTD the most accurate of the temperature sensors that we have discussed in this series of videos. The biggest drawback with these sensors is cost. These temperature sensors have a price of $25 or greater, which is why it's not available in the lab. Furthermore, if you were to use this device in your final project, a single RTD temperature sensor could take up a significant amount of your budget. In conclusion, here are the temperature sensors that we have discussed. We hope you have fun measuring temperature with these sensors.